Now we want to construct a graph of m of x equals x squared plus 5x plus 6 over x minus 3. You should do what you can with this, hopefully quite a bit, before you watch what I do. Okay, but having done that, the numerator is 0 when x squared plus 5x plus 6 equals 0. That factors into x plus 2 times x plus 3, giving you zeros at negative 2 and negative 3. I'm not going to write that out. Okay, but we have now zeros at negative 3 and at negative 2. When x equals 0, we get the y-intercept. The terms that have x as a factor will give you 0 when x equals 0. We'll get 6 divided by negative 3, which is negative 2. Also, the denominator is 0 when x equals 3. A 0 in the denominator that's not matched by 0 in the numerator is going to give us a vertical asymptote for reasons that we've talked about. And I indicate a vertical asymptote with a dotted line. And down here I'll give the equation of the vertical asymptote. Now, just to review just a little bit, a vertical asymptote occurs because when x gets close to 3, this gets really small. This doesn't. Okay, so if x is right around 3, not varying by 3 from 3 by, very much at all, the numerator is not going to vary a whole lot, but the denominator, well, if x is 3, it's going to be 0. If x is just a little bit less than 3, then it's going to be negative. If it's a little greater than 3, then the denominator is going to be positive. Now, the numerator is going to turn out to be positive here, but we'll figure that out. The numerator is not going to change sign, but the denominator, for values very, very close to 3, will sometimes be negative, sometimes positive, and at one value 0. To the left of negative 3, it's going to be negative. To the right of negative 3, it's going to be positive. How's that going to happen? Well, if we have an asymptote, if it's negative this way, it's going to do this. The other thing is, of course, when x minus 3 gets really, really tiny, which it does when x is really, really close to when x is really, really close to 3. Okay, again, when x minus 3 gets really, really tiny, which happens when x is close to 3, then you're dividing something really tiny into something that isn't, and you're going to get something that's really big. Now, it might be big positive, so it might be way up there. It might be big negative. It might be way down there. Since there's no limit to how tiny this can get, there's no limit to how big in either direction the result can get. So we say that the result approaches infinity if it's going in that direction, negative infinity if it's going in this direction. We've been over that, and we've talked about it quite a bit, and I hope people are beginning to grasp exactly why asymptotes occur, because it's kind of important to know. Okay, well, that's what we know. We want to determine where this function is going to be positive and where it's going to be negative. Now, the only way a nice smooth function like this can change sign is by going through one of the zeros, or by passing a point where it's not nice and smooth. And at x equals negative 3, it's not nice and smooth. It's going to jump from a huge negative instantaneously past 3, and all of a sudden it's a huge positive. So that's not nice and smooth, but that can happen. Now, it can also happen with some functions that it's got the same sign, either positive in both sides of the asymptote or negative in both sides. But that's not going to be the case here because of what we just talked about. Well, we can draw through light lines, a couple of light lines here, saying, okay, we got this region, we got this region, we got this region, and we got this region. The only place the function can change signs is here, here, or here. So everywhere in between here and here, here and here, or to the right of here, or to the left of here, the function on each of those four regions will have the same sign. It'll be positive in some, it'll be negative in others, but in any one of those regions, it's going to have the same sign. In each region, the sign is unchanging. Okay, so to the left of -3, what do we have? Well, if x is a big negative number, say -100, if you square -100, you get 10,000. 5 times -100 is -500. Well, that's not very big compared to 10,000, and neither is 6, so it's clear that the numerator is going to be positive. The denominator, on the other hand, if x is -100, you get -103, that's negative. So you'd be dividing a big positive by a negative. Now, you'd be dividing something about 10,000 by something that's around 100, but with the negative sign. 10,000 divided by 100 is about 100. So if you move over 100 units here, you got to move down because the result is negative, but you only move down to -100. In previous examples, you were going up to 10,000 or a million. Maybe -10,000 or -1,000,000, maybe positive 10,000 or positive 1,000,000. That's not happening here. You're only going to about -100. So the -100 that you put in gives you -100. The point -100 over here and -100 going down, the x and y coordinates are equal, so that's going to be at about a 45-degree angle. So we're going to say that, well, for large negative x, this thing is going to kind of approach a 45-degree angle. It's not going to go way down very fast. It's going to go way down eventually, but it's going to only do it without going down faster and faster. Okay, it's going to approach this 45-degree thing. Also, to the right of x equals 3, the same argument. You get something close to positive 100 in the denominator, something close to 10,000 in the numerator. You divide that, you get 100. So if you go 100 that way, you got to go 100 that way. Again, it's approaching, but it's approaching like a long 45-degree angle with the axis rather than getting very, very close to vertical. Okay. Now, between -3 and -2, let's take -2.5. Okay, if x is, well, let's think about it now. Well, now let's just go ahead and do it. If x is -2.5, then x squared is 6.25. You add that to 6, you get 12. 12.25. But 2.5 times 5 is 12.5. That's and it's going to be negative. It's going to be 5 times -2.5. So it's going to end up negative, it turns out. X minus 3, well, 2.5 minus 3 is negative. So you have negative divided by negative, which means that the function is positive here. Now, positive here, we already determined it's negative here, it's positive here. And it's got to be negative here. We already know that. Why? Because it's negative when x equals 0, and 0 is in this interval. And the function can't change sign within the interval, so it's stuck being negative. Because it's negative at one point, it's negative everywhere. Now, how can we draw a graph that's negative over here, but kind of comes up from something like a 45-degree angle? It comes up and it's positive here, but it hits 0 here and here. Goes through -2 here, and then it just kind of drops off the face of the earth with this negative asymptote. Then it's got a positive asymptote here, but it has to end up going in this direction. Well, we do that kind of like so. Doesn't come up very high here. Comes up along like so. Now, how can you come down from a high positive asymptote and end up going this way without going through the x-axis, because there are no zeros out here? Well, you can do that by just coming down like so. At some point you turn around, it's not clear where, and then you just head off to the big numbers. So the graph looks like this. We determine all that, again, this is at the precalculus. Precalculus level of reasoning. Now we're going to apply calculus to find the relative max and relative min. And clearly, we're going to have a relative max and a relative min. We're going to have a relative max here, a relative min here. How's that going to work out? First, let's draw our maximum point and draw our horizontal tangent line. So we have x prime of x equals 0 at your critical points. Critical points again being where the derivative is 0, where the graph levels off for at least an instant. And then f double prime of x, the sign of x double prime of x is going to tell us whether we have a max or a min. So we need to find this critical point and find this critical point. When we do, we're going to see that the second derivative for this critical point is going to be positive. The second derivative for this critical point is going to be negative. In order to do that, we have to take this derivative. So we have to find f double prime of x. But first we better find f prime of x. And it's not actually f. The function is m. So I'm going to pause, go off camera for a second, and change those signs. In the meantime, you should be taking these derivatives before you see me do it. Now I'm going to go to a different clip to do that.